Okay, we're all ready to decimate the room. Not many people left. Hardcore. Right, so up next, we have Polly McLean and Matthew Boyles joining us from IOM. They're going to talk to us about nano particles. Matthew, Polly, welcome. I don't know if you can see the room, but everyone's sat here eager and waiting for you guys. So I'm going to hand over to yourselves and let you do your presentation.
Good afternoon, everyone, and thanks to the organisers for inviting us to come and speak today. And apologies we couldn't be there in person. So we're, as I said, we're going to talk about nanomaterials, what they are, how we determine their risk, and how can we control them. So this may seem a far cry from LEV, but please bear with us as we wanted to discuss a topic which the organisers and ourselves thought would be quite interesting and relevant for you. And if you notice, one of the questions before the break was the use of real-time instrumentation and how this has an impact on the LEV. And this is actually what we use in a lot of cases. So I'm actually getting a terrible echo from the room there. I don't know if it's possible to switch that off. So we use real-time instrumentation in our day-to-day work, and that's partly what we're going to present today. So we don't use it in the context of assessing LEV. We use it in the context of measuring exposure. And one of the interesting comments or discussions that we had before the break was the use of this real-time instrumentation to assess behaviours, and that's exactly what we do in a lot of cases. So we might visit a workplace and we might assess releases, we might evaluate areas of high incidence, and we use this to determine whether LEVs are required and where they should be, and also to assess behaviours. And we do this by collecting contextual information throughout an exposure measurement. So this is something my colleague Polly McLean will discuss a little bit further on. So this is largely what we want to discuss today. We'll look at who we are, the Institute of Occupational Medicine, and what we do. And we'll go into details of what a nanomaterial is and why, or if it's a special case hazard. These will be done quite briefly. Then we'll go into how we evaluate workplace exposures to nanomaterials, how we control this risk to nanomaterials, and lastly, a few alternative approaches that can be used for mitigating the risk of nanomaterials.
Yep.
So I'll try to go through this quite quickly then, as we're now going to be a bit behind. So IOM, who we are and what we do. If you move through to the IOM slide, please, Polly. Thanks.
Perfect.
So we've been around for just over 50 years. We initiated with the study of coal miners' lungs. This was 50 years ago. That's the reason we were set up. And since then, our research has expanded. We still look at cancer, look at air pollution, look at chemicals, look at dust and exposure, look at musculoskeletal injuries, and we look at nanomaterials and different workplace effects around agriculture. In general, our purpose is to provide independent research evidence which informs policy and regulation. This is largely to improve occupational, environmental and public health, which ultimately has a positive effect on health of workers and the general public alike. So we've got, next slide please. So we have a number of different consultancy and commercial aspects to the company. We look at PPE, testing its effectiveness. We look at indoor air quality. We do ventilation testing, so we have ventilation engineers. We have occupational hygienists, and we do various consulting work, which could be looking at workplace hazards and exposures. And we offer training, so this is again in ventilation measurements. And we have laboratory services, which could be mineralogy or could be analytical chemistry. And we have research, which is where myself and Polly work, where we do work on human exposure, and we do work on toxicology, epidemiology, and human factors. So next slide, please, Polly. So we're going to briefly, I'm sure a lot of you already know what a nanomaterial is, but just for those who don't, we're briefly going to cover what this is and why it's considered at times a special case hazard. Next slide, please, Polly. So nanomaterial, as you'd imagine from its name, is particularly small. So if you go down this scale, you can go from insects of a few millimeters down to a human hair, which could be hundreds of micrometers in diameter, down to blood cells, which could be 1 micron, and then 1,000 times lower than this, you have a nanometer, and it's within this scale that nanomaterials lie. Next slide, please, Polly. So a nanomaterial can be defined as different structures. You could have 3 dimensions within the nano range, so a nanoparticle. You might have 2 dimensions in the nanometer range, so it'd be termed as a nanofiber, or you might have 1 dimension in the nanometer range, so it'd be like a nano plate. Next slide, please, please. And they're used almost everywhere these days. So in terms of different sectors that you find them, there's a recent study on the left here which shows the frequency in use in electrical equipment. I guess the next largest sector would be their use in healthcare, then energy, and then in construction, personal care products, and then a combination of various other industries, with some examples here on the right, including in sun creams. You'll find them in car tires, and you'll find them in medicines, and in phones, and in paints, and also in food packaging. So that they're almost in every industry. Next slide, please, Polly. And the reason, and it's been about 30 years, I think, since they first defined them as a special case hazard. So the exposure route can be any that you'd expect. It could be via the respiratory system, it could be via the GI tract, it could be dermal exposures. And I've just put up a couple of, we won't go into the toxicology work today because it's not the focus of the talk, but I just put in a couple of examples of the early studies that have demonstrated their effect. So on the left, you can see a schematic of the human respiratory system, where you have the different segments. So in the green, you have the bronchioles, in the red, you've got the alveolar region. You can see from the graphs next to this that the red zone, the alveolar region, you get predominantly deposits of material in the nanometer range. And then one of the earliest studies looking into this, so over 30 years ago, was a study on the right where they had nano-sized titanium dioxide represented in the blue, and larger titanium dioxide represented in the red. And this was an exposure to rat lungs. And what they found is that on a mass basis, you have a huge amount of toxicity, in this case, inflammation generated in the lungs in response to the nano-sized titanium dioxide over the larger titanium dioxide. Next slide, please, Polly. So that was a test basically on size, but since then, and over the last 30 years, there's been a huge amount of research looking into the different reasons why these materials can act their response, and it could be any one of different parameters which are outlined here. It could be their shape, it could be their size, it could be their crystal structure, composition, so they can be made of almost anything. They might have different surface areas and different porosities. You might have different functional groups on the surface. You might have a different surface charge. All of these could affect their toxicity. So we study these a lot, and myself, I look largely at toxicology, while my colleague Polly works a lot on exposure and measuring these systems, these materials in the workplace. And Polly will go on now to talk about the different methods that we use to measure and assess these in industry settings.
Thanks, Matt. So yeah, I'll briefly discuss how we'd evaluate the risks to nanomaterials. So to start with, I just wanted to go over the exposure pathway. And again, this might be something that's very familiar to a lot of you in the room. But I wanted to point out a few things specific to nanomaterials. So you could get emission from many different processes that involve nanomaterials. Of highest concern from our kind of studies and also in literature are any processes that involve the use of dry powders, so things like weighing, mixing, sieving, and any operation that is of high energy, so cleaning and maintenance operations, machining such as sawing, grinding, polishing, any process that would involve spraying liquid dispersions of nanomaterials, and also things like incorrect disposal and accidental spillage. And once nanomaterials are aerosolized, they will remain suspended in the air for far longer than larger particles. So where your micron-sized particles might just remain suspended for a matter of minutes, nanomaterials have been shown to stay in the air for hours or even up to days. And that's a really important consideration when we think about the control measures, which I'll discuss a bit more later on. And much like any other dry powder, we get a feedback mechanism between the air and surfaces. So once they are deposited on surfaces, they can be re-aerosolized. So again, that's why I'd want to avoid any high energy processes or any cleaning operations that's going to resuspend those into the air. And as Matt said, you get various different exposure routes to humans. So inhalation and dermal are the main ones, but you can also get ingestion as well. One of the main issues really with controlling exposure to nanomaterials is that there's no occupational exposure limits set in regulation. Currently, we've only got recommended OELs, and these are kind of based on the usual mass-based concentration units, really only for nanomaterials that are well studied and that their hazards are well known. So for example, here we've got carbon nanotubes, fullerenes, silver and titanium dioxide. But for those that their hazards are maybe not well known, there are a range of recommended OELs that can be used that are just widely based on the nanomaterial property. And these are based on particle numbers per volume. And to measure that, we'd use this integrated sampling strategy, which I'll go into a bit more detail now. So basically, to conduct the integrated sampling strategy, we need to really focus on three different pillars. So we've got the real-time instrument measurements, offline chemical analysis and microscopy, similar to what would be conducted for typical chemicals, and also contextual observations that we would gather on site as well. So to start with then, the real-time instruments, what's their purpose? So you could basically use quite a range of instruments now. I'll go into a bit more detail about those in the next slide, but you can get the option of quite portable handheld instruments, although these typically have limited size resolution, or you can get more sophisticated benchtop instruments, which are still somewhat portable. They have the benefit of having a greater size resolution, but are typically more expensive and more difficult to use. So with these instruments, we would measure background concentrations. That just gives us a baseline that we can compare against. And then for our airborne concentrations at the emission source, you're really wanting to focus on what is the question you're trying to answer. So you can sample the area, so you can get kind of job-related task-based measurement. You can also use that to investigate whether your control measures are working sufficiently. Or we can also look further at personal breathing zone, so you can get full shift measurements that would give you personal exposure, which you'd be able to compare against those OELs that I showed in the last slide. And as I said, you would compare the emission source to the background concentrations to determine if you've got any significant release. So as I said, there's a range of different instruments available. I've just selected a few here that are quite commonly used. So for the portable instruments, I've just selected 4 here just as an example. They all operate on kind of different size ranges, often different measurement methods. So here we've got typically optical measurements, but you can also have electrical charging. And the majority of them will measure in particle number per volume, but you also have the option of, say, the dust track, which also measures as a mass-based concentration. And then the more sophisticated benchtop instruments, as I said, are a bit larger, and so we typically get a bit more in-depth information from those, so better size resolution. So you can see from some of these, the size channels that you get range from 14 to 217, so you can get quite a lot of detail in the particle size distribution. And these all typically give you an output of particle number per volume of air. And as well, they all have different measurement methods, slightly more sophisticated than the benchtop, than the handheld one, sorry. And the main issues that we face across the board with these instruments basically is that they're not specific, and so have to be supplemented with offline analysis. So what I mean by that is if you were on site and you were trying to determine what personal exposure was to, say, titanium dioxide, these instruments wouldn't be able to tell you exactly how much titanium dioxide was in the air, only the total number of particles in a size range. And they also typically assume spherical particle shape, which can give you kind of skewed results in terms of the sizes, especially if you're looking at things like agglomerates or platelets or fibres. And I just wanted to include an image of our typical site setup. So as you can see, there's quite a lot going on there. It's not very mobile. We typically need to use a trolley, and this will have to be connected to a plug, so it's not very mobile. So we do have to utilise tubing, which you'll see on the top there in black, conductive tubing that we can connect to the outlets of all the instruments, and then you'll be able to direct the flow to wherever you'd want to assess, so whether that's the breathing zone or at the process itself. And so what information do we get from these instruments? So as I said, most of them give you particle concentration as particle number per volume of air. And they typically measure on a second by second basis, and you can edit that for most of the instruments. You can make it kind of longer period if needs be, but it does give you that kind of real-time information, so you know what's happening as the process runs. And as you'll see here, we've got different peaks on the graph on the left-hand side, so we would match that up to the contextual information that we would be taking on site. So you can see here we've got sections where we're sampling in the breathing zone, and so we can give an assessment of whether there's a release at different areas of sampling. And then we can investigate those peaks further for the more sophisticated instruments that give you particle size distribution. So the graph on the right here just shows what we would typically do. So we can kind of take the time point where the peak occurs and give a relative particle concentration. And that just gives us the particle size distribution at that time. And then you can use that to compare against background. So are you just getting a higher number of background particles, or are you seeing a different distribution of particle sizes, which would kind of indicate you're getting a release that's different from the background. Okay, so moving on to the offline sample measurements, as I said, these are needed to supplement the real-time information because it's not specific for particle types. And so to do that, we would implement processes that are already happening in occupational hygiene practices. So similar sampler types that you'll be aware of, so cyclones, IOM heads, cowl samplers. We also been utilising TEM samplers, which are fairly new, where you can deposit directly onto a TEM grid, which makes it far easier for doing the TEM analysis. And the analysis types that are recommended always include some form of microscopy. It's really the only way currently that you can fully identify as a nanomaterial. And then you could supplement that with other kind of chemical analysis like XRD and ICP, and that can give you a concentration of all, say, titanium dioxide that's on your sample. So it gives you that kind of mass-based concentration that you could compare against the OELs. The main issues that we are finding for doing analytical techniques for nanomaterials is really detection limits. That's one of the main ones. So because of their small size, a large number of particles still doesn't really amass to a large mass of particles. So you need really low detection limits to get that sensitivity that we would need for nanomaterials. Also, sensitivity of instruments. This is typically an issue for microscopy techniques. So if you've got quite a homogeneous sample, if you've got larger particles on your sample, so micron size, that'll really mask the signal that you can get from microscopy, so you can often not get that resolution that you need at the nanoscale. And one of the main ones as well is obviously the cost of doing microscopy analysis. So you really want to focus your sampling strategy so that you're possibly not taking as many samples as you would be able to for a mass-based concentration. And then to finish off this section, then how would we report the results? So we'd need to take all three pillars from our integrated strategy and to kind of combine them all together. So you want to look at the offline analysis together with the direct reading instruments and the contextual information. And it's kind of summarised in this table here. So we take the summary of those results and it'll give you a probability of exposure. And just to note as well, the cutoff value that we use for the direct reading instruments is based on those background concentration values that we've measured, which I highlighted previously. Okay, so moving on now to controlling the risk. So if you've identified that there is an exposure, you may need to take steps to control those risks that you've identified. And basically how we would do this is similar to what you would do for normal chemicals, basically focusing on the hierarchy of control. So you want to go from the most effective control measure down to the least. You don't want to be focusing on only PPE to keep you safe from nanomaterials. So if I first go over the recommendations for engineering controls, the basic principle is that you want to have a kind of barrier between workers and nanomaterials just to reduce the risk as far as reasonably possible. So the HSE recommends the use of LEV to enclose the process as much as possible. And there's lots of really good guidance from NIOSH which gives some good examples specific to processes. I've just added in some images here from the NIOSH guidance. But there's examples which include chemical fume hoods, handling enclosures, safety cabinets, glove boxes, those types of things. But crucially, the exhausted air should be HEPA filtered and wherever possible vented to a safe place outside. One of the examples that we often give is a site visit that we were on where the LEV was working sufficiently. We didn't get a release during the machining, but there was a subsequent release later on when the air was recirculated into the environment and hadn't been sufficiently filtered. So it's really important that the air is filtered when it's exhausted. And then moving on to administrative controls. So as I said previously, we want to avoid any processes that's going to result in re-aerosolization of dry powders. This is important for cleaning processes, so we'd always recommend using a HEPA filtered vacuum cleaner or wet wipe cleaning, and never to use a brush or compressed air, as that'll just re-aerosolize the particles and they'll just deposit back down again. There should be sufficient safety warnings and signage in the areas where nanomaterials are used, and access should really be restricted only to those workers who are required to be in the area. All nanomaterials should be stored in robust labelled containers, and all workers that would be involved in any nanomaterial processes should have sufficient information, instruction and training. And finally, any waste that's produced should be disposed of as hazardous waste, purely because the hazards are still largely unknown for most nanomaterials. And then finally, personal protective equipment. So as I said before, we don't want to rely on PPE for nanomaterials. It should really only protect you if everything else fails. But the guidance that is given for use with nanomaterials are overalls that wouldn't have any risk of retaining any nanomaterials or any penetration of nanomaterials. So polyethylene is given as an example rather than paper or cotton. Similarly, for gloves, the recommendation is to wear 2 layers to prevent any penetration, and also just allows you to ensure that you can remove them well without any secondary exposure. You should have close-fitting safety glasses, and RPE should have an assigned protection factor of at least 40. And as I said, you don't want to use PPE as your primary protection measure because basically it's uncomfortable to wear, and therefore people won't wear them correctly, and there's typically a problem with compliance. And so with that, I just wanted to mention some further reading materials that I would recommend. So HSE have a really good guidance, it's the HSG 272, and also NIOSH, as I said, have a range of different guidance documents, and they're quite good because you can get one specific to different operations. There's lots of examples of control measures that can be used for nanomaterials. And finally, the one in the middle here I think is quite good, which is just questions to ask before you start, and just gives you that kind of quick guidance on what you should look up, and is quite good to kind of display in any labs that are using nanomaterials. And so with that, I'll pass back on to Matt.
Thanks, Polly. So much of what Polly's discussed is measuring and controlling the risk of exposure once somebody's already working with nanomaterials. But there are some approaches that can be used, and if you have clients that are concerned about using nanomaterials, there's a lot of concepts which can be addressed and thought of prior to them starting any work. So we've just kind of laid out 3 examples of stuff that we're working on currently that helps in these matters. So this can be looking at guidance for safe handling procedures. This can be applying a process called grouping and read across, which helps to predict a hazard with limited testing. And there's thirdly the use of a safe by design approach, which is becoming particularly popular at the moment. Next slide, please. So there's lots of guidance which we've already made you aware of, and this is something else which is, I guess, a slightly more holistic and pragmatic overview of a safe handling procedure. So it's put together by the UK Nano Safety Group, which is a collaboration between higher education and research councils and industry groups and government departments. And it's really aimed at any number of people, including employers, managers, health and safety practitioners, but also those directly working in the lab. And it's guidance that gives support in the safe and responsible working practices with nanomaterials. And it covers a wide range of aspects, including largely what the official guidance gives, where you're looking at hazard concerns and exposure concerns. It looks at risk management methods, including different tools that can be applied and PPE that's required and engineering controls that are suggested. And it's also supplemented with case study information related to certain perhaps high risk or high production nanomaterials. So there's been 2 additions to this. The third one's coming out shortly. And then there's a grouping and read across approach. This is basically an approach that allows a different risk assessment approach. So whereas you have a conventional risk assessment of could be chemicals or nanomaterials, and they're largely very expensive to perform, they're very time consuming, where you have to assess a hazard potential of a substance, where you're looking at testing toxicity and hazard endpoints, defining a concentration that causes this effect, and then finding a way to control releases to that low hazard level. And this largely uses a lot of animal studies, which is frowned upon. So the grouping approach allows you to compare substances based on their physicochemical properties or their toxicological behavior. And it's even supported by REACH for chemical grouping. So if you find a material that has a similar physicochemical property or a similar tox endpoint, then you can reliably group these with similarity testing, and it allows you to put a regulatory decision on something without doing extensive testing. And we've been involved in a project called Gracious, which is setting up a framework that allows you to do this for nanomaterials. And it puts together a quantitative assessment to support grouping of nanomaterials for submission in regulatory dossiers. Next slide, please. And again, there's quite substantial guidance on this. So if you wanted to know more, you can come to us, or you can look at this guidance by ECHA, also by the OECD. So it's quite a heavily supported area of work just now. Next slide, please, Polly. And lastly, we wanted to bring up safe by design. So again, before any of your clients may want to use nanomaterials, or before they want to incorporate it into their processes, or they're concerned about an exposure, there's a process called Safe by Design, which again is supported by the European Commission. And it's basically set out to allow you to assess safety, allows you to assess the sustainability of your product, allows you to maintain high performance of the product, and allows you to compare costs to make sure it's a cost-effective process. Next slide, please, Polly. And we're involved in a few research projects that are helping to develop platforms that allow industries to use this effectively. So this is one of our projects called Sabina, where we plan to set up an e-infrastructure that allows you to, or helps you with risk identification. It helps you to establish sustainability and cost impacts, and it allows you to have mindful interventions. So if there's a potential hazard, or there's a potential in high exposure or high release, it gives you interventions that prevent this from occurring. And this is currently targeted at the paints industry and the 3D printing industries. So that's all we wanted to go over today. I think there's a Q&A question later on, which myself and Polly will hang around for. I think there's another speaker, and we can wait until that last session to answer any questions that you may have.
First question from Vox. Is it right that nanomaterials tend to agglomerate as the separate particles are charged and tend to bulk up with others to create larger form particles, and therefore lowering the inhalation risk?
Yeah, completely, absolutely. So I think generally in the aerosol, you'll have quite a mixture of surface properties, including charge, and it's been measured that you get these negative and positive charges, which means in the air they do agglomerate, and they do form particles that are either too large to be inhaled to deep lung regions, or they're too large to be maintained in the air. But conversely to this, you can have a substance which is pretty homogeneous in its properties, in that sense that there is a risk that they do retain as primary particles, and then there is a risk of exposure. Interestingly enough, I think due to them defying the laws of gravity, nanoparticles can remain as an aerosol in the air for quite some time. I think Polly might know better, but I think it's a matter of days they can actually be maintained in the air if they retain a primary particle size.
Thank you very much. Another question. So as you guys noted, fume-covered exhaust should be H14 HEPA filtered. Page 12 of HSG 272, the NANO guidance, states at least one HEPA H14 filter when you're talking about recirculating. What exact number of HEPA filters is recommended by? What does at least one mean? 2, 3? Do you guys have any experience or research findings on that?
No, unfortunately not. We don't have any ourselves. I think at least one is what's recommended, but obviously, yeah, it depends on the system and whether you could implement it. You guys probably know a bit more about that than we do. I think one is typically sufficient. We do use HEPA filters to do QC checks on our instruments, and typically HEPA filters does take the particle number down to almost 0. You will get some that possibly pass through, and obviously depends on the lifetime of your filter. Obviously, if you've got more, I guess that will extend the lifetime as well. But no, it's not something we've looked at further. It would definitely be a really interesting project for us to take on. Would definitely be interested in doing that, but yeah, I don't know if there's been further studies on that. Not anything that we've been involved in.
Thanks you guys so much. It was just a couple of questions, unless there's anything from the audience before we move on to Kevin. Nope. Okay, well, thank you. I thought this would be such a great talk. Our theme is where the future is headed. The LEV industry is only going to get more and more involved in nano, so I thought this was like perfect for the theme. So, okay, well, thanks so much, you guys. You can sign off, and up next we have Kevin or